Hello everyone, I am Walid Djema from INRIA Sophia Antipolis in France. My today's talk is about competition between microorganisms. In particular, here we focus on the issue of minimal time selection of microalgae species in a chemostat system. So this is a joint work with Olivier Bernard, a senior researcher at INRIA, and also Terence Bayen, a professor at the University of Avignon in France. Microalgae are photosynthetic unicellular microorganisms of great diversity, since there exist nearly 1 million different species. Microalgae are essential for life, since they fix 50% of anthropic carbon dioxide. They can be used, for instance, for producing proteins, pigments, antioxidants, or essential fatty acids with several applications. At longer term, their use for carbon dioxide mitigation and bioenergy production has been also considered. However, their biotechnological use is still very young, and in practice, only a few wild species are used among the large biodiversity of microalgae. The main challenge is to select, in artificial cultures, some more productive species with better characteristics. Selecting and improving these microorganisms is, however, challenging due to their complex interaction with their local environment. A classical model that describes microalgae dynamics is the Droop model that improves the basic monod model by introducing the extra dynamics Q. The quota Q quantifies the internal substrate storage of the microalgae species that consumes the free nutrients S, while X here is the biomass concentration of the microalgae species. The growth functions mu depend on the quota variable. And finally, the dilution rate d is the bounded non-negative control function of the chemostat. Now, we are considering the case where several microalgae species are competing in chemostat. Selection by Darwinian pressure, so by imposing conditions that favor the species of interest, has already given some spectacular results. These continuous selection approaches are, however, time-consuming, and we can expect to improve these experiments using optimal control, especially by playing on the dilution rate of the photobioreactor. So, the objective of our work is to identify optimal strategies, minimizing the operating time when the species of interest dominates the population. Now, let us consider the previous Drops model, but now it involves two different species, X1 and X2. Each one has its own quota Q, and both are competing for one limiting substrate S. Sin is the constant input concentration of the substrate, and D, the dilution rate, is always the bounded non-negative control function of the model. We are going to add some extra conditions on the classical growth and absorption functions in order to ensure the well-posedness of the optimization problem. More precisely, we define this function delta as the difference between the effective growth rates of species 1 and 2. The effective growth rates are derived at equilibrium from the initial functions of the model, mu and rho. And as we can see, the effective growth rates depend on the variable s. Now, we assume that this function delta can be both positive and negative, which actually reflects the fact that both species may win the competition. We also assume that the upper bound on the control D is larger than the effective growth rates in order to avoid any abnormal truncated control. So, thanks to these standard assumptions, the studied problem can be stated in a generic framework. The optimal control problem of interest is stated as follows. Firstly, we define the target set, T, that expresses the fact that the species of interest, x1, is larger than x2, with a very small parameter epsilon quantifying the contamination rate of x1. The objective is to determine an admissible control law, D, that steers the model trajectories towards the target set T in minimal final time, denoted here by TF. Here we give the Hamiltonian H associated with the optimal control problem, as well as the necessary optimality conditions derived from the classical Pontryagin maximum principle. The resultant costates dynamics are given in form, and thanks to the transversality conditions, we prove that these dynamics satisfy the conditions that the costates of S and the quota variables, Q1 and Q2, are both 0 at TF. We also prove that the costate of x1 is strictly positive, while lambda x2, which is the costate of x2, is strictly negative at the final time TF. Moreover, since H is linear with respect to the control D, we deduce that according to the sign of the switching function, tilde phi, the control is bong 0 or bong D max. And using the transversality conditions, we also find that tilde phi and its first time derivative are both necessarily 0 at the final time TF. Next, we notice that when the switching function is 0, for instance, over a time interval t1, t2, the control is singular, which is denoted here by ds. In order to determine the singular control ds, we compute the second derivative of the switching function tilde phi, and we also check the Legendre-Klebsch second optimality condition. Indeed, the Legendre-Klebsch condition in this case is always satisfied along the singular arc, thanks to assumption A1 previously stated. Under these conditions, we can determine ds as a feedback of both the state and the costate, which is given here in 6. Thanks to Pontryagin principle, and by analyzing the singular arcs together with extensive numerical simulations, we can state that the optimal control structure is Bong singular for a large set of initial conditions, including the typical case where the initial concentrations of x1 and x2 are equivalent. This is partially justified by the fact that the switching function, tilde phi, as well as its first time derivative, are 0 at TF, the final time. For other initial conditions, the structure of the optimal control can be of Bong type or Bong singular type, and this situation is particularly observed when the initial conditions are close to the target set T. Now, we illustrate the most common case in which the optimal control is Bong singular using a direct optimization method implemented in Bocop. In this case, the contamination rate, epsilon, is fixed to 0.05. And we notice also that the initial conditions of x1 and x2 are equal. Here are the functions resulting from the considered model parameters. The function delta satisfies the required assumptions, and SC around 0.08 is the substrate concentration maximizing the function delta. The optimal control given by Bocop is the following one, which starts with the Bong d equal to 0, then there is a switching instant, and then the singular arc, ds, steers the model trajectories towards the target set T. In this case, the trajectories reach the target after nearly 18.9 days. At the final time, TF, the ratio between x1 and x2 is maximum, which is in fact 1 over epsilon, as illustrated in the figure on the left that gives the optimal model trajectories. The co-state trajectories, on the right, satisfy the optimality conditions, and particularly the transversality conditions. There is one switching instant in the control, and it corresponds to lambda s, the co-state of S, equal to 0. Moreover, we notice that a turnpike-type behavior appears in the trajectories of S, Q1, and Q2, as well as in their corresponding co-states. In particular, we highlight that the trajectory of S evolves most of the time around the constant Sc, maximizing the function delta. So, in this work, we discussed theoretically and numerically the issue of optimal species separation. We provided a strategy to select the species of interest in minimal time in the Droop model. And in future work, we will focus more on the analysis of the singular arcs in order to better understand their role in the structure of the optimal control. Thank you for your attention.